Hello everybody, I'm Derek Hitchins. I'd like to talk today about the differences between systems engineering and the engineering of systems. So, what is the difference? Does it matter? And who cares anyway? Where to start? Probably best to start with what is a system. That's what all the fuss is about, fundamentally, isn't it? There's no agreement about the nature or even the existence of systems. A complex, organised whole or body of material or immaterial things, said the Oxford Dictionary of 1946. We'll take that as a starting point, because that allows a system to be real and tangible, or, for example, a set of or arrangement of, say, ideas, theories, practices, etc. A system. Even that definition can create arguments. What is a whole? How do you know when you've got one complete? What does organised imply? Why complex? What do you mean by complex? System is a human perception, cannot be real. Yet we have the solar system, and we have self-organised systems like you and me, with our organised organ systems, ecosystems, enterprises, and so on. So, engineering of systems. Is a car a system? Well, that rather depends on your point of view. Is it complete? If so, then it might be a system. If it's incomplete without the driver, on the other hand, then it's an artifact, a machine, an implement or a tool. Or, only a system when complete with driver. When together they become a viable, autonomous system. And that would be the system scientific viewpoint. Does the designer envisage the car as a machine of many parts, with seats and controls for a driver, or does he view the driver as an integral part of the total system? Engineering of systems starts from a requirement, a specification that in effect describes how the end product, or is it a system, should look, operate, behave and interact. To use the jargon, fit, form and function. And the environment in which it is to be maintained and operated, with threats and risks engendered by that environment. Its performance, durability, reliability and maintainability in those environments, and so on. This is, in effect, classic engineering, building to customer specification, but done properly by engineers. And it has no effective way of dealing with any human element in the system. So humans are generally outside of the so-called system. They're viewed as adjuncts, plugins, and interfaces. So how is SE, systems engineering, different? Well, systems engineering does not start with the customer's requirement. Instead, systems engineering may start with a customer brief, researches the customer's problem, and establish what the customer really needs, rather than wants, to solve his or her root problem. It uses a variety of skills: problem solving, system science, social science, management science, operations research, contingency planning, resource management, causal loop modelling, dynamic simulation, brainstorming, nominal group technique, interpretive structural modelling, functional elaboration, architecture design, mathematics, purposing, specifications, and so on. Plus, a large chunk of domain knowledge and skills. And the domains vary. It could be defence, transport, command and control, digital communications, IT, air traffic management, emergency services, industry, famine relief, medicine, and so on. Being potentially innovative and creative, systems engineering may come up with novel solutions to the customer's problem. And SE, systems engineering, proves that any proposed solution will solve, resolve, and dissolve the problem in context and environment. We'll see what those three terms mean later. In one highly contentious but very important respect, systems engineering is different. An objective view of systems engineering would suggest that it is not engineering, at least not in the classic sense. An engineer is, by definition, one who designs, builds or maintains engines, machines or structures, qualified in a branch of engineering, especially as a professional, e.g. an aeronautical engineer, or an electronic engineer, or a hydraulic engineer. You disagree? Well, systems engineering addresses people systems, social issues, ecosystems, enterprises, processes, management systems, organisations, etc., plus socio-technical systems, defence, aerospace and power. And the skills involved in systems engineering may include operations research, problem solving, architecture, physics, biology, management, organisation, psychology, mathematics, dynamics and simulation and anthropology, which taken together go towards system science, but not really engineering, except in the less usual sense of the term. Skillfully arrange for something to occur, as in to engineer a situation. So systems engineering really isn't engineering, although it can define what needs to be engineered and what does not. Systems engineering brings less complex systems together, integrates them to synthesize more complex systems with requisite performance, behaviour and survivability of the whole in some operational environment. It approaches the conception and creation of people systems, socio-technological and technologically based systems in the same way, concerned with the whole, how parts contribute to the whole, functionally, behaviourally and structurally. It's concerned with subsystems performance, behaviour, interaction, mutual interdependence, cooperation, coordination and contribution to form a unitary whole, performing optimally in its operational environment. It is, importantly, reduction-free. No part or subsystem is viewed in isolation, only in and as part of the functioning whole. So conceptually, philosophically and practically, systems engineering is quite different from engineering per se. To consider it as engineering, and the exclusive province of engineers, would be seriously misguided. It is better viewed as applied system science, at which some engineers may excel. The essence of systems engineering is in 1. Choosing the right parts. 2. Bringing them together to interact in the right way. And in orchestrating those interactions to create requisite properties and behaviours of the whole, such that it performs with optimum effectiveness in its operational environment, so solving the problem that prompted its creation. In each following case, the parts or subsystems function in relation to the whole. The parts are mutually interdependent and the whole is integrated and unitary. First, the radar comprises of transmit, receive, detect, locate, track, identify, tell modules, and of course power and maintenance. An enterprise consists of marketing, research and development, production, sales, admin, human relationships, and a board of directors or similar. And the most obvious example of an orchestra: strings, brass, woodwind, percussion, and of course a conductor to bring them all together. Notice, particularly from C, which makes things rather obvious, how each part has to work in cooperation with and adapt to the other parts, so that the whole is an integrated unit. For many problems, customers know very well what they want, or should it be need, as solution, and are well able to specify the requirements. In those cases, there is no need for systems engineering. Engineering of systems or buying off-the-shelf, commercial off-the-shelf software, COTS, will suffice. You don't start a development every time you want a new car, for example. For some problems, the solution may not be so obvious. The customer may face a dilemma, seeing many ways, or perhaps no way, to solve a problem. But which is best? And what does best mean in the circumstances? Could there be an alternative that is even better, cheaper, more harmonious? Requires justification, perhaps, for a major outlay on an uncertain project. The customer may have an existing solution but want a new variant to operate in a new domain, environment or context. In all of these and many other similar cases, engineering of systems is insufficient. You need systems engineering with its innovation, creativity, complexity management and its solve, resolve, dissolve philosophy. Besides, engineering of systems presumes a technological solution which may not be required. So how does systems engineering work? It employs a methodology, which is a system of methods and rules, with expert people who know how to apply them. The systems engineering methodology follows the systems approach. It observes system principles and uses systems methods. Systems methods are scale independent, system type independent, and context independent. And the systems approach views the world and its problems as interacting systems, which may be modelled, simulated to show behaviour over time. And it employs system principles of holism, synthesis, and organicism without any reduction. The systems methodology can, in principle, address any problem or problematic situation, no matter how large or small. Although in practice, some tools, methods, and expertise may be needed appropriate to particular domains. Systems, methods, and tools stimulate creativity, innovation, and harmony within and among domain and systems engineering expert practitioners. And systems engineering, with its unique principles and practices, does actually appear to be a separate discipline in its own right. I said that I would explain solve, resolve, and dissolve. And here we are. You can see here a conceptual model of a systems methodology. It starts on the left-hand side with some issue or problem, which is evident because problem symptoms emerge. The problem is explored, explore problem space. There are remedial solution concepts are formed, and a synthesized whole solution is designed as an ideal world. So the idea here is to use the problem symptoms to create some ideal world design, which is then compared with the real world model, which we know because we know about the problems. Now, the ideal world has no problems, the real world does, and by comparing the two, one can see the difference between them, and from that you can create an ideal world solution, which would be an optimum solution system if you're solving the problem, or an acceptable solution system if you're resolving the problem, or satisficing, to use the jargon term. There is a third approach, as you can see at the bottom of the diagram there. One of the other ways of solving the overall issue is to change the real world. And we call that dissolving the problem. In other words, you change the context and environment such that the issue or problem no longer occurs. This is a method that politicians are very fond of, and it's very economical. However, just taking the three there, we start with an issue or a problem and we end up creating either an optimum solution, which is called solving, or an acceptable solution, which is called resolving, or we change the context or environment such that the problem no longer occurs, and that's called dissolving. Three possible ways of going about dealing with the problem. Systems methodologies were developed by different organisations over many decades, largely through trial and error, to be honest. There was, however, convergent evolution. These various organisations ended up producing the same processes and procedures using the same or similar systems method and principles of creativity, some of which are given here. Highest level of abstraction, disciplined anarchy, breadth before depth, functional before physical, tight functional binding, loose functional coupling, those two refer to architecture, and functional migrates to physical. Let's look at levels of abstraction. It's important at the outset of one of these exercises to avoid jumping to conclusions and jumping to solutions. So one has to employ the highest level of abstraction, what is needed. So if the need is for transport for a small family, that could be a taxi, a bicycle, a bus, a train, a plane, or anything. It's not specifically a 3-door Toyota RAV4 as shown in the photograph. That is not the highest level of abstraction. That's very particular. Similarly, if there's a problem with accidents, the solution is not an immediate 20-mile-per-hour speed limit, but some way of keeping vehicles and pedestrians apart. And an intruder alert is a little more abstract, shall we say, than an automatic machine gun to address intruders. We may not need a new radar so much as some way of detecting smugglers, or hotspots, or drugs, or stowaways, or distant planets, or alien life forms. So level of abstraction is considerably less specific, and that's to avoid jumping to conclusions at the beginning of the exercise. Function first. The conceptual system will have purpose and will perform functions to pursue its mission, to manage its resources, and to maintain its viability. There will be sensor, motor, processing, organizing, and managing functions, setting objectives, formulating strategies, communicating and cooperating functions, surviving, defending, reconfiguring, self-healing, maintaining, coordinating, evolving, keeping dynamic equilibrium. All of these will be functions too. All of the functions of the viable autonomous solution are first identified, then organized into a functional architecture. The functional architecture is migrated and mapped onto a physical architecture, and that's how it proceeds. I mentioned systems engineering principle. The first of these is holism. Systems are viewed as wholes, not as collections of parts. Systems function as wholes, and their functioning cannot be understood solely in the terms of their component parts. Synthesis, combinations of parts or elements to form a connected whole, which is the opposite of reduction as used in some sciences, engineering of systems, and engineering. Organicism. Systems resemble organisms in having parts that function in relation to the whole to which they belong. And you can see at the right there a diagram showing levels of organization and integration, going from cell or component at the bottom to community at company at the top. Each of the levels in the hierarchy is synthesized from the level below, both columns. So systems engineering considers the whole of the customer's problem, creates a complete viable autonomous system solution. And EOS, engineering of systems, may have an important part to play in designing, developing and making specific parts of the whole. But could there be rather more to it? For example, should the robot be autonomous, have empathy, morals, ethics, a conscience even? Should it have the ability to reproduce? A very controversial subject. And are these engineering issues, or issues for systems thinking, systems engineering, or even Stephen Hawking, who has been commenting on just this ability to reproduce? In the diagram you can see the sort of things that would be going on in the mind of an intelligent robot. It would be pursuing some sort of mission, and you can see the mission management cycle at the top. It will be collecting information through its sensors, assessing situations, setting itself objectives, strategizing and executing its plan and cooperating with others. And its behavior is similarly involved in that there will be a stimulus which it will recognize, interpret, and will select behavior according to the stimulus and respond. That's a stimulus response arrangement. And you can see in there's a belief system which influences how it recognizes things, it influences its behavior. And in there are morals, stereotypes, ethics, doctrine, training. It's really rather more to it than simple engineering. There indeed is a generic reference model for a viable solution system. And you can see the things I've been mentioning in the 5 panels. There's a resource management panel at left, a viability management panel at right, a message management panel at top, a behavior management panel in center, and the form, where all the physical structures are, at the bottom. All 5 panels are active and operational simultaneously. You can see also that you can use models like that to represent complex systems. Here we have 2 viable autonomous systems in conflict. Systems engineering incorporates, as part of the exercise, operations research. And this would be simulation in assistance to sort out operations effectiveness, operations performance, concepts of operations, and so forth. Returning to systems engineering versus EOS, in systems engineering we have this problem, system design, specification, integration and test, and then the end product. We can see that we start with a complex problem space at the left, then we go system design, starting from the abstract information we've got about the problem, and gradually producing ordered, structured, refined. You can see configuration entropy dropping under the system design process, and then producing a matching set of requirements which result in procurement, engineering, purchase of equipment or acquisition of equipment, facilities and training. And from that we end up with the 3 things that we're going to deliver: a mission system, a user operator training, planning and tactical support system, and a maintenance and support system, so that the mission system is maintained and it is supplied with trained users and operators and continually updated tactical support. Of course, that assumes that the mission system has other systems supporting it separately. Quite often these days, they're all in the one, and we get something that looks more like this: an independent viable system, where mission management, resource management, and viability management are all in the one housing. Examples of that would be a robotic peace officer, a sort of automated Robocop, a planetary explorer, a nuclear plant engineer, that's an automated engineer, and the much touted independent warrior. Let's look at classic systems engineering as it was back in the 70s and 80s. You can see here, this is somewhat old-fashioned now, but it gives you the general idea of how systems engineering has been done in the past. We start off with operations analysis, then requirements analysis, then system design, which specifies the needs of equipment engineering and software engineering, then integration and test of the equipment and software, and finally installation and commissioning. And you can see from the arrows that there is a lot of iteration and feedback. There's arguments about whether engineering and software engineering are part of systems engineering. It is largely historical. In the US, engineering was part of in-house systems engineering. In the UK, on the other hand, systems houses contracted engineering out to engineering companies. So in the UK, engineering was considered to be completely separate from systems engineering, whereas in the US it was considered part of it. As a result, we still have a hangover about what fits where. Continuing that a bit further, systems engineering then came under these phases: operations and requirements analysis, system design, and then equipment and software engineering, which we've discussed could either be part of systems engineering or not. We've shown it here as part of it. Test and integration, and installation and commissioning. Equipment and software engineering developed 5 project subsystems, and you can see them listed below. There was the primary mission system, which the customer wants. There's an in-service maintenance system to support that for the customer. There's an in-service training system for users and operators and maintainers of the mission system. Now, Also, there's an in-company engineering system needed to develop the first three. And that engineering system is also subject to problems, so there's an in-company maintenance system to keep the in-company engineering system operating. So there are a total of 5 systems to produce the 3 that are delivered to the customer. This is an example taken, as it shows, from the aerospace domain. And there, I won't go through this, but you can scan through that and see the various disciplines and skills that were required in each of the areas. You might be surprised to find how many of them are not really what you'd call engineering. This is a model produced by Behill and Gissing in 1998, so after the previous one. And this is quoted by Nkosi as the basis of an iterative system engineering process. And similar stands for state the problem, investigate alternatives, model the system, integrate, launch the system, assess performance, and re-evaluate. Similar falls rather short of being a systems methodology. There is no way of exploring and solving the problem, and no system design. It does not apparently take the systems approach, and it relates principally, it seems, to engineering technological products, to specification time, budget, quality, and requisite life cycle. Interesting to show as a process. Although there's so much iteration, I'm not quite sure what the process is. So, systems engineering versus engineering of systems. Where have we got? Systems engineering explores the customer's problem, conceives a solution, and creates and delivers or commissions a complete, viable, autonomous solution. Engineering of systems undertakes any technology development and manufacture that may be required as a part of the overarching systems engineering program. And there's our original questions. So what's the difference? Well, systems engineering and engineering of systems are fundamentally different, conceptually, philosophically, in method, principle, and application. Does it matter? It matters greatly that the exceedingly powerful potential of systems engineering should not be overlooked and lost. Nkosi will, no doubt, develop systems engineering methodologies, or simply systems methodologies, in time, but they're not yet in evidence, while the need for a modern systems methodology to deal with today's and tomorrow's increasingly complex and chaotic systems continues to grow. And who cares anyway? Anyone with sense. Systems engineering is a proven way of bringing our best brains to bear on difficult and important issues and problematic situations, and for creating viable system solutions of all kind. Psst, want to put a man on Mars? And get him back by the end of the decade? Are you worried about population growth, global warming, globalization, terrorism, large-scale IT, asymmetric warfare, integrated transport, our dreadful education system, decivilization, and so on and so on? Perhaps you need systems engineering. Thank you for listening.